Hello and welcome. I will talk about the optimizing game networking in C++ because pretty much I see more and more custom-tailored games and systems that are just slow on this part. So let's talk about how to actually get a proper performance and how to do it somewhat right. Okay, so starting off, we have that every byte is actually fighting for the latency, and the scale, it just adds up because pretty much you can see that the code scales with players times relevant entities that we want to update. So it's O(n) times m pretty much. And what we want to know is that whether or not we are using the UDP, which is typical for most games because, well, TCP is too slow. It could be used for some turn-based games where there's no like collision of inputs between many different clients or players, but still it depends. So most likely it will be UDP, where we can have a packetless, where everything should be a bit faster and a bit better for the experience, but we need to take into consideration that, well, it's with losses. Then we are not snapshotting every single thing each frame. We are updating only the necessary things. So pretty much we need to take care into the consideration of the updates. And also we need to take care of the round trip budget. So every single basic thing counts. So now let's dive into how exactly it should work. So first off, we have the authoritative server and snapshot model. And what happens is that we have the client, it sends a specific input and predicts it locally if possible. It sends it to the server runs the simulations, resolves all the collisions, and the server sends the snapshots to all the clients so they can just send the render state, update the interpolations, and whatever it is related to the game or the systems that you're running on. And now for the somewhat of the optimizations, because sometimes you can have some latency issues, some bugs, whatever it is. You have the client-side prediction, which is pretty much simulating the client ahead of the server. We have the interpolation buffer, so pretty much whatever we are doing is happening, for example, 100 milliseconds in the past. So whatever packets that we drop are actually not stopping and lagging the game, but we are still running through. So the redundant send, for example, of the UDPs could actually catch up and show the different simulations to different clients. Of course, it's not that we are playing with 100 milliseconds lag. It's that the some of the simulations around us could have a 100 millisecond lag if it's not that much importance to us. So we need to take care into consideration of that. And also there's reliability and unreliability. So pretty much the state that we're sending is unreliable in UDP, and a specific event that needs to be reliable no matter what, get a custom layer for that. And now we have 6 levels of shrinking. So first off is that we can imagine that, for example, we have a position, right? For position, we could have 3 floats, so 12 bytes on most systems. And because we have those 12 bytes, well, first off, do we actually need to send all the 12 bytes because we moved somewhere? Well, not really. The movement is quite slow. Like we are usually moving by a very small amounts of values, like between, for example, -10 to 10 or -100 to 100 or -1000 to 1000. And it's way smaller than what 4 bytes of float can cover. So what we can do is, for example, send 16-bit float, so 2 bytes for each. And then maybe we don't need a certain one for the Z. So we pretty much want to do the quantization. So pretty much map the values into a certain smaller ranges. Then we want to do a bit packing. So for example, we can think in bits that the Z value actually would require 2 bits. For example, the booleans will require 1 bit, not 1 byte. And then we go into the delta compression. So we only want to send things that need to be updated this frame. So for example, a client did not move at all, he didn't do anything, right? There's no point to send anything from him. Like every single client will just simulate the same thing that there was, and there's no point to send additional data. So we only update the delta, so the differences. Then we have the interest management, and this is the thing that we only want to update the things, so only the things that are around our player, so around us. We don't care about something that happened miles away behind the mountain or whatever, because it does not concern us. It's like important to the players that are around it. It's not important to us. So we want to have a grid or whatever spatial algorithm that will tell us what's important to us, what's near us, what's going on. So we can make the relevant entities to update as small as possible, like the set of them. So it's pretty good for us, right? Then we have the prediction and reconciliation. So what we want to send is actually not the state. So we don't want to send every single data about transformation, every single data about a certain spell. No, we want to send the input. So for example, if I move, so I can move in a three-dimensional space, I need to have three floats. But what if I can only move forward or to the right, for example, and it can be forward, backward, right, left, but from one value, so pretty much two floats, and we can't go up, down. If up, down, then another float. But again, it's just an input, and it can be smaller, like it's just an information. It could be even in bits that we are moving forward this frame, and based on the velocity of the player, that can be hard-coded or also sent in some quantized bit-packed way. We can have a very minimal amount of data that is required. The same goes, for example, for animations. Someone pressed a button, we just sent a bit that, this guy is entering this animation state. It's just one bit. It's nothing like more, nothing less. That's about it. And then we go into the entropy coding. So to put it short, there are certain algorithms in some networking theory that, based on statistics of how the game is used, how much data is sent, what's going on, defines how important certain data parts are, how unimportant others are, and based on that, it says what's the actual limit of data that we need to have, so the range. So it's not like random worst case that we might think of, but actual case that happens, so that we have the minimal possible amount of data that we send between client and server. And this is like the beauty of it. So we send the crazy small amount of bits and the optimizations go through the roof. Just to show the quantization and bit packing, pretty much you can imagine that we want to write a certain value with a certain bits. We have an option to quantize it. And here, for example, we want to have a float 32, but we map to a smaller range of motion that does not need 32 bits of coverage. So we can, for example, create a 50% smaller size per axis. So this is one of the many ways to do something, and it's one of the great ways to do something. Then we go to the delta compression. So pretty much for the baseline, we first off update every single thing because, well, we need to tell what's actually going on the first, but later when we do the ticks, so the updates each like frame or networking frame, because it might differ from what's actually happening with the actual simulation. We, for example, only say that on the frame 41, we changed a certain field, on 42 the same, or 43 the same, and 44 nothing happens. So we don't update anything. So we only update the things that changed and need to be changed, right? Quake 3 did great things, like Valve has a lot of source on that. There are also a lot of great people who says a lot of things that can just show you how to optimize everything related to it. Then we have the self-healing on loss. So if a certain delta is pretty much lost, because, well, we are using mostly UDP, so packet loss happens, the client just keeps using the older frame, and the server simply diffs those two until there's a resync. So this is how we pretty much do it. And then there's the interest management. So we can imagine that, as I said, that something can be behind a mountain somewhere and we don't really care about it, so it's not interesting to us. So we only replicate things that are near the client, so near the player. And that's what pretty much is happening in most games that know what they're doing, or that use engines that know what they're doing for them, in most cases, of course. And, well, we have, for example, a potential invisible set. So we can have some pre-computed data to call anything that is not related to important things. We pretty much use some spatial algorithms like spatial hash. It could be also an octree, whatever it is. And pretty much we rank things by the relevancy budgets, so how much data we can send this frame, and also for the priority, so we can rank things by the importance. We can just hardcode some values like how important something is, then by distance, then by whatever else we want. And this is pretty much how we tell that something should be replicated or something shouldn't. Then we have the prediction and reconciliation. So pretty much first we sample the input. So someone pressed a button, someone pressed something on the mouse, or moved the mouse, or moved something on a joystick, whatever it is. And then we send the inputs that are need to be sent, and we predict them locally. So we want to say that we probably will move somewhere but we need to take into the consideration that the server might lose some packets, whatever can happen, and then the server simulates whatever input we send to it, and then it sends back the results of the simulation, and we reconcile, so pretty much check what's going on with client and server, and if there's any delta, so we can actually snap to correct values depending on the inputs, right? So the prediction happened, because sometimes we need to take into the consideration that, well, there might be lags, and later we check if the prediction was what the server also simulated, and if not, then we go back to the server. Well, in most cases it will be fine. In some other cases we'll get a big jump, so we just use it because it helps with like worse networking. Then we have the compressing rotations, so the smallest three. So let's say that we want to use the rotations, the quaternions or whatever it is. Like a naive quaternion will be 128 bits on most hardwares, and because it is normalized as a unit, we can drop a lot of stuff and rebuild it on the server and client side. So pretty much, if there are no changes to the quaternion, or if there are even small changes, we can drop the largest component. We can also send 2 bits of index, so we can encode a certain data around it. And we can also do the quantization of the components of the quaternion. So for example, you can imagine that instead of the float, let's say we have the rotation, right? Well, what we realistically need could be even a 1 byte. So 0 to 255, and then you can use a values between 0 and 180, and then whatever is the data that you received, you just multiply it by 2, and the loss of the plus minus 1 doesn't really matter. Players don't really see them. For you, it's way less data to send, so it's great. And then you can also bit encode it, so it's even smaller when you sum it all. So pretty much there's a lot of ways to compress this data. And then we have the entropy encoding. So pretty much what we do is at the last compression step, use certain statistical algorithm to just tell how big certain things should be, depending on how often they are updated. For example, in Morse code, we have a reason why certain letters are shorter to write and others are longer, because, well, things that are used often should be smallest and simplest to use, and the same applies to the networking data. We can find the smallest possible amount of bits to use something and then figure out how we can use it. So pretty much first we quantize something, then we bitpack it, then we only update the deltas, and of course also we check what's important to us, and then we entropy code it. And then we have the unified read-write serializer in C++. So this is like an example of what could happen by, for example, Glenn Fiedler, great guy. Here we can see that we have a structure with a player state that has like a position, rotation, health, and Boolean whether or not he is firing. And well, now you know that the Boolean can be just a bit. Now we know that the integer, depending on how big it should be, for example, here it's 100, so it can be just 7 bits. So it's 1 byte now with those 2 variables. Without it, we could have, for example, 2 bytes because the health was uint8. So 1 byte less. Then we go into the rotation and we can also quantize it. And depending on how much data we need from the rotation, because it varies from game to game, it could be, for example, 2 plus 3x9 bits, which is way smaller than 128. And then we can also use it on the position, which also could be way smaller. And this is like one of many ways how you could optimize it in the stream that you send over the network. And pretty much how the titles put it together. So we have the Quake3 Arena that did the snapshot data compression against like clients act frames, and we have the Huffman coding of the whole stream, so pretty much as optimized as possible with statistical analysis. And pretty much later every shooter game borrowed that. Then we have the source engine with Counter-Strike, Team Fortress 2, and there we have the delta compressed entities over the baselines, client-side prediction, interpolations, and lag compensations. And the networking of Valve became a great reference for the industry. Then we have, for example, Overwatch, where everything is entity component system driven, so pretty much very optimal, very cache friendly. And then we have the frame sync replication, and only the relevant thing in high bandwidth mode. And things are sent as minimal commands, so it's not like you send the whole ability of everything that happens around it, but only very small inputs of what's going on, the command of it. So like those are the typical ways of how to do it. And then we also have, for example, Rocket League, where you have deterministic network physics with bit-packed replication. it fits in a very, very optimal state for the few players that they have. And pretty much when we stack the techniques, you can see that we're for 64 bits, where we could have some row floats. So let's say we have a typical double, right? 8-byte double. First, if we quantize it for whatever we want to use, we can have, for example, 38 bits. Then if we use the bit packing for whatever we want to use, it could be 28 bits. For in this case, I just have, for example, entity that could have a position, rotation, velocity, and few flags. And well, then we only check for what's actually updated. And out of those 28 packed bits, we only update 14. So we only send 14. And now we also check statistically what should be the ranges. So we add the entropy for that. And if we find out that it's 9. So instead of sending 64 bits, we send 9 for literally the same thing that we would update. And it's great when you think about it. And now we just have a very simple checklist of what do we want to do with the bandwidth. So pretty much we want to quantize every continuous value to the minimum perceptible precision. So pretty much the smallest possible thing that is visible to us, because, well, we don't care about anything else really. Then we want to delta compress against every snapshot. So we only want to update the things that actually change and then test if the prediction and what's the authoritative server update, whether or not they are updated in the same manner. If not, the client has to change depending on the server update. Then we want to only send the inputs and prediction and reconcile if they are not related, as I said. We want to serialize everything in a small bit width. We want to replicate only relevant stuff around us. So as I said, with the spatialization of the areas. And then we want to compress the rotations with smallest free and entropy code the stream at the end of everything, so that based on statistics, we have the least amount of data possible to send. And then for the go deeper, there's stuff from Glenn Fiedler, Valve Developer Wiki, and ID Software stuff that is great, and I recommend to read that and check it out. So yeah, thank you guys for watching, and I hope you have a great day. Cheers.